Right. So yes, there's an interesting problem I want to discuss from section 11.5. Here's a problem. This is then start from 1. Okay, this is an alternating series. All right. Now there's you can even modify the problem. You can modify this problem. For example, turn this upside down, right? N factorial on the top, n to the nth power in the denominator, for example. Okay, so we can also look at this one later. Okay. Right. This is alternating series. Does not mean you have to use the alternating series test to prove it's convergent. Maybe it's divergent. So you first we have to make a simple observation. You let the Bn to the n, okay? So does it, it's positive, right? So first question, first you have to check, does it approach 0 or not? Okay. Does it approach 0 or not? Well, you can take a look at all the terms, right? The denominator is 1 times 3 times 4 all the way to n. The numerator is n times n times n all the way to n, right? So clearly, this is bigger than 1. Do you agree? Yeah, it's bigger than 1, so it never approaches 0. So you cannot apply alternating series test to prove it's convergent. Okay? Actually, this limit Bn, in fact, Bn approaches positive infinity. I'm not going to prove that, okay? All we needed to know is Bn does not approach 0. That's enough. So since Bn does not approach 0, and this one even does not exist, okay? Of course, it's not going to be 0. It does not exist. Why doesn't it exist? Because Bn does not approach 0. So negative 1 to the n is just up and down, does not approach 0, okay? So therefore, the series is divergent. And by what? By the nth term test. Nth term test is only for divergence, okay? That's it. Okay, then how about this series? Okay. So this time, I think this is going to be well, this approach is 0. Okay, how can I show that? Okay. First of all, it's positive, right? This is alternating series, right? I also have to prove that it's decreasing. Maybe it's not easy to prove it's decreasing. So let's prove this approach is 0. So for n, you see, let's write down this, right? Every term here are less than equal to 1. I only keep the first 2 terms. So when n greater than equal to, okay, this is less than equal to 1 times 2 is n times n. So it's 2 over n squared. Okay. 2 over n squared. So that's why, to prove this is an approach of 0, I just need to keep the first term. Okay, so I don't need yeah, that's all we need, right? Okay. So this is approaches, it's less than equal to 1 over n because the rest of them less than equal to 1. So this approaches 0, therefore Bn is 0. Now the question is why Bn is decreasing. I have to check the following, right? Bn plus 1, right? Bn plus 1 I want to prove this is a less than Bn, right? Less than Bn. So this is a Bn, right? It's less than equal. Let's simplify it. Let's simplify it. Yeah. So this is going to be n plus 1 to the n plus 1. Here's n plus 1 factorial. And right, let's simplify. We want to make sure this is less than equal to 1. Then it's decreasing, right? So that is going to be n plus 1 factorial. Okay, over n plus 1 to the n plus 1 and n to the n factorial. Okay, so let's simplify it. N plus 1 factorial over n factorial, just n plus 1, right? And then I have n to the nth power. So then here n plus 1, here's n, right? So you simplify, right? Then finally you get n plus 1 to the nth power. So that's just simplification. If we go to algebra, you can do that. And what is inside is less than 1, right? So it's 1. Clearly, then Bn plus 1 is less than or equal to Bn. Okay, great. Therefore, this series is convergent by the alternating series test. And I'm going to go back to this problem again later, okay? We are going to learn some new method to prove it's convergent. All right. So today's section is about the following theory. All right. So this is the theory. The theorem says that if this series has absolute value of of any other terms, this is a convergent, means it's a finite, then this series is convergent. Okay, and why this is true? Why this is true? Okay, this is not obvious. Okay, this kind of series is we because it's always guaranteed. So in this case, we also say that this is absolutely convergent. Okay. All right. Now I need I skip the proof here. It's given in the book. Okay. The idea is a follow. You know, using actually one of the proofs is using so-called Cauchy sequence. You look at the partial sum. Okay. You look at the partial sum and as a sequence, and you have to prove that sequence convergent. I think use the original definition. Okay. You have to show that and. Yeah, so we're going to use this to do the following. We accept this thing right now, okay? So you go back to this series again, okay? So this is my n, okay? This is my n. So I take a look at absolute value, Okay, and then you have an n factorial of n to the nth power. Now, only when all the terms are now negative, you can use a comparison theorem, a comparison test. Now, this time I do need you write down all the details here. 1 plus 2 times 3, right? All the way n times n times n. Okay, so you have to make sure n is greater than or equal to 2. So all those terms less than or equal to 1. So I get less than n squared. So this is true when n greater than 2. Since by the p-series test, right? This series defined by this term is going to be converted. Okay, so yeah, you can say start from n2. Okay, this is a finite by the p-series test, right? P is going to be 2. Right, you can let p to be 3, you know. Then you have to have an n cubed. Okay, so that implies this one is finite because, yeah, this is a finite, right? So this is therefore, by the above theorem, n is convergent, right? Right, so it's in this in life. Okay. Now it is possible the series is convergent, but it's not absolutely convergent. Okay, the absolute value of all the terms, add them together, maybe infinity. Okay, so in that case, we can say that it's only conditionally convergent. So there's a difference here. Okay, there is only two. Okay, first of all, case 1. Yeah, this is divergent, right? And if it's convergent, but absolute, not absolute convergence, then we say it's absolute. Yeah, that's the first case. Second case is convergent, but this is a divergent. In this case, then we say that this is a conditionally convergent. Okay, sometimes. Okay, so convergence, we want to say a little bit more about convergence. Okay, if a series is convergent, maybe it's only conditionally convergent because it's not absolutely convergent. Okay, a good example is this one. Okay, and here's P, and the P is less than or equal to 1 greater than 0. All right, so this is a conditionally convergent. Why? Yeah, this is a convergent, but not absolutely convergent. Okay, so it is convergent, but not absolutely convergent. Okay, it's not absolutely convergent. So these two combined, we call it conditionally convergent. If we want to get more information about the series. Okay. Why it's convergent by the alternating series test? Okay, because the nth term decreasing to 0. This part. Okay, this is by the alternating series test. Okay, but not absolutely convergent is by the p series test, because when you remove the negative sign, right? Okay, now we are able to study this problem, cosine n over n squared. I think about how to say this is convergent or divergent. Okay, and give a proof. Right. So look at this. First of all, cosine n. Cosine n changes sign sometimes. So it's not necessary. So this is another alternating n. This is not even, I cannot tell if it's alternating series or not. Okay. But it can be negative sometimes. Okay. So I cannot use comparison test directly or use any of them. Okay. Yeah. Please, if you're able to find a way, please do it. Okay. Give me a half a minute. To drink some water. Okay, now let's go back to this problem. So the only way we can solve this problem is to prove it's absolute convergent. Of course, it is convergent. Okay. So this is my n. So I take absolute value, and now every term is non-negative. Okay. So this is going to be less than 1 over n squared. And by the comparison test, you have this inequality, and this is a finite, and this side is by the p-series test, right? Okay. So that means this series is absolutely convergent. Of course, it's convergent. We have to quote that theorem. So that implies is absolutely convergent. Now, you don't need to say that always. If we just want to prove it's convergent. Right. The reason this series, okay, let's go back to the theorem. It's the proof of the theorem. The key idea is as follows. You look at the partial sum, right? You look at the, yeah, let me mention the proof of the theorem. Just a few sentences. Okay, that's enough. Okay. First of all, every term, okay, can be written in the form n plus minus n. Okay, clear, right? Obvious. Okay, then I look at the partial sum. Okay, and an, right? This is partial. I want to prove this is convergent. Okay. Okay. Now, by assumption, this is convergent, right? Okay. So by assumption, yeah, let me just put a key here instead of infinity. Okay. Yeah, this is a partial sum, right? By assumption, this is a convergent. convergent. Okay. Now, let's take a look at this term, Bn. This Bn, okay, is n plus absolute n, right? Do you think it's negative? No, it's never be negative. Okay, when n both are positive, this will be 2n. When n is negative, this can be 0. So it's either 0 if n is negative, or 2n if n is greater than or equal to 0, right? Okay. So we always have this, right? Because when n is positive, and I even can put a absolute value here. So doesn't matter, right? Yeah, this is always like that. Okay, then use a comparison test, right? N equals capital N, Bn. This is going to be less than or equal to. Okay, this is a finite, right? That's by assumption. This side is by assumption. Okay, so that means this is also convergent. Okay, all right, so that's it, because this will be the difference of two convergent sequence, a series. So that's why this implies, right, that implies the limit, okay, is going to be okay. So both are, finite here, so that is convergent. Okay, so that is this is pretty tricky, okay, argument. Okay, but we use a comparison test to prove that. Okay. All right, so now now let's take a look at another problem. So let's go back to the alternating series. All right, so this is a n squared plus 1. All right, maybe you want to put the absolute in here. Okay, sounds like. Okay, so take a look at this. What is the best way to solve this problem? If you're given this problem, okay? If you're given this problem, Yeah, think about it. All right, this is alternating series. So it's natural to use alternating series test, okay? But the difficulty is, right, you have to prove this is decreasing. Is it easy? Not that easy, right? Not so easy, right? You have to prove a couple things. One, Bn decreasing. Two, Bn approaches zero. Approaches zero is easy to see, but decreasing is not easy to prove. Okay, it's not easy to prove that Bn is decreasing. Okay, it's not easy to prove. But you can, right? But it's not easy. So what I'm trying to do is, this is my n. So I consider the absolute value of n, which is just a square n squared plus 1. And then this is less than or equal to square n squared, right? And that is going to be 1 over n, 3 over 2. Okay, so that is my new series, gives me my new series. Okay, so so the absolute value of this, okay, is less than or equal to, okay, and this is a finite, okay, this is a finite by the p-series test, okay, by the p-series test. So that implies the series is absolutely convergent. So that implies, and it's not only convergent, this is absolutely convergent. Okay. So much easier, okay, to prove this convergent. Not convergent, it's absolutely convergent. All right. Now, the reason we want to study absolute convergence is because we are going to have two important theorem. One is called the ratio test, as one called the rotor test. Okay. So the ratio test. Okay, the ratio test. We assume that this is a, yeah, we assume that this limit exists. Okay? But it can be greater than 1, can be less than 1, could be 0, no, it can be 0, okay? So L is, can be from 0 to infinity, okay? So first, if L is less than 1, then you can show that this is a convergent, okay, is finite. I just say finite, okay? So then the series is absolute convergent, right? So if L is greater than 1, or infinity, right? Including infinity, okay? Then this series is divergent. Okay? And then when L equals 1, inconclusive. Okay, you cannot say anything about this. Okay, so this ratio test has a limitation. Even the limit exists. Okay? If it's 1, you cannot say anything. Okay, so here's the example. Okay, the proof is simple. Okay, let's say I'm going to prove proof of a case when L is less than 1. Okay, let me show you how to prove that. When L is less than 1, okay, this is because the limit is L. So then you must have, here's 1, right? Here's L. So you must, for sufficient large N, the ratio will be less than this, right? So I take an arbitrary number between L and the 1, okay? So this is less than or equal to L for N greater than capital N, okay? For some large N. All right, so that's it. And then what do you get? Then you will get, multiply this out. And it's less than or equal to L times L times L. How many L here? I think I'm going to have N minus capital N plus 1, okay? But all of the terms will be canceled out. Okay, what is left? I think here's the next one is AN plus 2 of AN plus 1, right? So those will be canceled out. What is left is N plus 1 and less than, it's less than LO N minus capital plus 1, okay? So I can simply write, and the row to the N, this little n minus capital N plus 1. I'm going to put it into here, and that's a low capital N minus 1. Here's a low to the n's power. All right, I can put this one here, and that's only capital N, okay? So that is true for N greater than capital N. And then you're using the comparison test. Why? Because this is N, right? Capital from N to infinity, right? It's less than or equal to, this is a constant, don't worry about that. Okay, and by the geometric series test, this is a finite, okay, because the low is less than 1, okay? So that means the series is absolutely convergent, okay? So that implies this series is absolutely convergent. Okay. We compare a geometric series, compare with the geometric series. All right, so let's take a look at some examples. Okay, and this is the example I want to talk about. Remember this problem, right? N factor over n to the n's power. Maybe we can prove this, okay? Okay, this is my A, okay? All right. All right, so how do I do that? Well, I already showed you how to do it before, right? We proved that it's absolutely convergent. We have proved that this is absolutely convergent. But to use some trick, you know, right? Some tricks in mathematics, right? We prove that absolute of an is less than or equal to 2 of n squared, n greater than 2. Then we prove that it's absolutely convergent. Okay, right? Yeah, this is the first method. Method number 1. Okay, now, not everybody can figure out this. All right, so this is we compare with a p-series. Right? This implies, right, let me repeat this again. If we can figure out, this inequality, then you're done, right? Then it's absolute convergent, right? Then it is absolute convergent. Right. All right. The second method, we consider this ratio. Okay. This ratio, it is going to be, forget negative sign, right? So n plus 1 to the n plus 1. Here, n plus 1 factorial. Right. And actually, this we use to prove it's decreasing, remember? Yeah, this is n factorial of n to the n's power. So after we simplify it, so here's n plus 1, n factorial, n to the n's power. So after we simplify, we get this. Right. Now the question, what is the limit? What is the limit? It's less than or equal to 1, but what is the limit? So you have to rewrite this in another way. It's going to be n plus 1 over n to the n's power. So we get a very familiar term. We have the important fact, the limit as n approaches infinity, 1 plus 1 over n to the n's power is a number e. Okay, so that's why this approaches 1 over e, which is less than 1 as n approaches infinity. Okay, so you get a limit. The limit is less than e, 1 over e. The limit is 1 over e, but less than 1. Okay, so that implies this is convergent, okay, by the ratio test. Now, the ratio test is not a universal test. When I was grading the previous tests, I found out something just only learn the ratio test, use that for all the problems. And that is not good. Okay. Okay. Some simple series cannot be proved convergent. It is convergent by ratio test. For example, problems like this, 1 over n squared. I know it's convergent by P series test, right? But if you want to use a ratio test, what do you get? The ratio test, right? It's going to be 1 over n plus 1 square 1 over n squared. So you get this. Now, what is the limit? The limit is going to be 1. The limit is going to be 1, okay? It's not going to be the 1 over e. It's a 1. So inconclusive by the ratio test. So you cannot use a ratio test to say anything about that. Okay. All right. So take a look at the next problem. Okay, and I even can put a negative sign here. Okay. This is looks like an alternating series. So what is the best way to solve this problem? Yeah, think about that. I'll give you 1 minute, okay? If you figure out 3 different methods, great. All right. So some of you were trying to prove its alternating using alternating series test, okay? So let's see. This is my Bn, okay? I want to prove the Bn decreasing to 0, right? Okay, let's try. How do you prove this is decreasing to 0? Okay, you still have to look at the ratio, right? Decreasing, and y is decreasing to 0. Okay, n factorial grows faster than any exponential function. That's clear. Okay, so let's see if I can show that. Here's n factorial 100 to the nth power. After I simplified, well, great. This is just 100. This is n plus 1, right? Clearly, this is going to be less than 1 if n is greater than or equal to 99, right? Okay, so indeed, this is going to be decreasing if n is sufficient large. That's enough. As this is decreasing, n greater than or equal to 99. The second, I have to prove this approaches 0. So Bn equals 100 to the nth power. So first of all, this is a pretty big number, right? So I'm going to choose larger one. 1 times 2 times 3 all the way to n, right? So here's 100, 100. So I'm trying to assume n is greater than 100. Let's say 100, 100. Okay, I'm going to assume that n is greater than 100. So this is again be 99, right? And then 100, 100, right? And then here's 100, and this is n, right? What I need is, I just need the last 2 terms. Right? For the rest of them, this is a well, there's three parts here. One is this part. This cannot be changed. And from 100 to n minus 1. So maybe I should choose, at least I have to have two terms. So n should be greater than or equal to 100, 101. Okay. Then the rest of this part always less than or equal to 1. So what I got here is less than or equal to 100 to the 99. Here's 99 factorial. That's a big constant. Then here's n minus 1 times n. Here's 100 squared. Okay, so clearly, no, 100 is enough because I just want to prove it's convergent to 0. So, yeah. Okay, it's 100. Okay, so I need all I need is the last term. Okay, I need this term. I don't need the rest of it. Okay, so clearly this approach is it. Okay. I drop all the terms in the middle. This is all less than or equal to 1. Okay. If there are any terms there between 99 and the n. All right, so that's it. So this is use it's not easy, right? Use the alternating series test. Okay, this is the first method. Okay, we're trying to use many different methods. Second method, use alternating, use a ratio test. Okay, you consider this ratio. Okay, we already simplified this ratio, right? So it's going to be, you see, it's easy to see that after you simplify, just 100 over n plus 1. So clearly the limit is 0, which is less than 1. Right? Therefore, this series is convergent by the ratio test. Okay? Another important test is called the root test. It's very similar to the ratio test ideas. Okay, so you consider, you assume that the limit L exists. This is the nth root. Okay, exists. Okay, it could be infinite, okay? And this could be finite, right? Or positive infinity, okay? So the first case is if L is less than 1, then the series is absolutely convergent. Okay? And actually you compare with the geometric series again. So if L is greater than 1 or infinity, right? Then actually the nth term does not approach 0. So that implies it's divergent. Okay. So actually the nth term is going to be positive infinity. Okay. So that implies the series is divergent. Okay. When L is greater than 1, okay, not, and when L equals 1, it's inconclusive. Okay. Yeah, this, of course, this implies the series is divergent. Okay. Now, this series is useful when there is no term factorial, n factorial. Okay, so we don't know. Yeah, this term is this ratio test is useful for terms without n factorial because the nth root of n factorial we don't know. Okay, so I have to put a remark here. Okay, you don't know what is that. The infinity or finite, right? But we know. Yeah, we know the limit of the nth root of n. Okay, we find the limit, the nth root of n. Okay, how do you find it? Okay. So nth root of n is going to be e to the nth root of n as a natural log, right? So this is the natural log of n to the 1 of n, right? So that's going to be, that is going to be n natural log of n. So natural log divided by n, the limit is going to be 0. Okay, so that's why this approach is 1. So we have the following fact. So what? I believe that this will be infinity. So it's not easy to prove. I can show you how to prove it, but it takes time, so we don't need that. So in general, it's harder to find the limit of nth root of n factorial. Right? Okay, let's take a look at some examples in the book. I'm not going to prove again. I'm not going to prove that this theorem. Okay, very similar. Okay, to the ratio test. Okay, let's take a look at the following example. Okay, and here we have to decide what the value is. This is convergent. Okay. Determine the variable a such that this is convergent. So you can use a ratio test. You can also use a root test. Okay, so let L to be the limit and nth root of an absolute value, right? N squared, because maybe it's negative. Right? Right. Let's find the limit. this limit, I want to tell you this absolute A. Why? This is going to be, right? Right? And the numerator is just A. So denominator is going to be n, 2 over n, okay? So that is going to be actually n to the 1 over n square. So 1 over n, or n to the 1 over n approaches 1. So it approaches absolute A and the 1 square, which is absolute A, as n approaches infinity. Okay. So clearly, if absolute A is less than equal to 1, less than 1, then this series is going to be convergent. Is absolutely convergent. Right. So using the ratio root test, you can jump to this conclusion. Now, if this is greater than 1, then this series is divergent. Right. The question is, what happens when n equals 1? When a equals 1, absolute A equals 1. Okay. So let's take a look at those two cases. If A is going to be 1, okay, my series is here is going to be A to the nth power n squared, right? I think we should use the theorem we studied at the very beginning. So this is going to be absolute A to the power n squared. Absolute A is going to be 1, so it's 1. And this is a convergent, right? So that implies this series is convergent. So the original series is absolute convergent, okay? So that is absolute convergent. Great. Okay. So use you can use alternate. You can use a root test to check the most of cases, right? Then when absolute A is going to be 1, you just look at these specific cases. Okay, you can use you can show that this is still absolute convergent. Okay. Now, can you use a ratio test? Yes, I think you can still use a ratio test. Right, the limit is still going to be absolute A. So more in most cases, you can use a ratio test if you can use a root test. Okay, there are some cases it's better to use a ratio root test or ratio test. So it depends on problem. Okay, so when you see n factorial, it's better to use a ratio test because n factorial can be easily canceled out. Okay. Okay. All right, so let's go back to this problem. Five to the n 3 to the n, 4 to the n. Wow, that's pretty straight, right? So what is the best way to solve this problem? Can you use a ratio test or can you use a root test? Or neither of them? Yeah, please think about it. Okay, so let's go back to this problem. And this was one of the problems on the final exams, previous final exams. Can you use a ratio test? Very complicated. Use a root test, it's harder to simplify. Only the numerator, because there is a denominator here. So actually, you just use the nth term test because some looks like you can, some series looks like you can use a ratio test or root test, but does not mean you have to use that. Okay, so this is going to be. I want to make, I don't think it's approaches 0. Okay, what I'm trying to do is, 3 and 4 are different, so I make it same. So 3 to the n is less than equal to 4 to the n. So now I have the same term, right? Okay, and then I take it out. You see? Then I can simplify, right? And the 5 over 4 is greater than 1. So clearly, the limit of an is going to be infinity, right? Yeah, because it's greater than or equal to some number which goes to infinity. Therefore, this series is divergent. by the nth term test. Right? All right, so now let's take a look at the next problem. This is n factorial 2 to the n squared. Wow. Look at that. Remember, I told you before, if you see n factorial, okay, don't use the root test because you cannot easily find out the nth root of n factorial, right? So what are you going to do? We simple. All the terms are negative, right? Non-negative. So this is n, it's non-negative. So there are many tests you can use, okay? Question is, does n approach 0? If n does not approach 0, it's already divergent. Quick. But I cannot tell whether this is a divergent. Okay? I cannot tell what is the limit. Okay? I don't know. At this moment, I don't know. It's not obvious. The reason is, now this is true, okay? This is true. If n factorial over 2 to the n, this is going to be infinity, okay? That is infinity. Does not mean 2 to the n squared is infinity because this grows much faster than the denominator, okay? Right? This is a fact, okay? So can we use a comparison test? I think it's not easy, comparison test. Compare with what, right? It's better to self-compare, compare, just like when you want to compare. You compare with yourself, it's okay. You compare today's life with previous life, last year, right? Oh, my salary is increased. But it's harder to compare with somebody else because you don't know what the other people's life, right? So comparison, yeah, you imagine. So this is a ratio test is compared with the term, previous term. Then it's always there. So let's find out the limit. Consider the ratio. Okay, right? And I want to find out, I put up absolute value. Put the absolute value. Okay. Put the absolute value there because even it's not it's always positive because that's the origin statement. Right? So let's try to simplify it. This is n plus 1, so n plus 1 factorial to the n plus 1 square. And the denominator, right now, I can turn it upside down. Okay, let's simplify it. So this will be n plus 1 factorial, n factorial. And this will be n squared 2 to the n plus 1 squared. And here is n plus 1, right? How about the fractions here? Well, you can move it to the denominator. So n plus 1 square minus n square is going to be 2 to the n square, so 2n plus 1. I think this is going to be 0, approach 0. Okay, because the numerator is exponential, numerator just is n plus 1. So denominator is 2 to the n plus 1. It's an exponential function. So clearly this approaches 0. Okay, this approaches 0. Okay, so that means the limit of n plus 1 over an is going to be 0. So which is less than 1. Okay, by the ratio test, it's absolutely convergent. But anyway, all the terms are non-negative, so it's this, you don't need to mention that. It's convergent. Okay, it is convergent. Okay, so use a ratio test, you can easily solve the problem. And yeah, this is ratio. So that means if the denominator, right now it's not 2 to the n squared. So 2 to the n squared grows much, much faster than n factorial. So let's go back to the chart. Natural log of n grows much, much slower than n to the n epsilon. And slower than to the any a to the nth power. Here's a is greater than 1. That's epsilon greater than 0. And less than or equal to n factorial. Okay. Now we have another picture. It's going to be less than a to the n squared. Okay, this is maybe less than or equal to n to the nth power. Okay. Yeah. So depends on which one is on the top. Okay. Right. So that we guarantee, yeah, n factorial over. Yeah. So that means this is a this is a convergent. Okay. But if I put the a to the n squared, a to the n squared, then it will be divergent. Okay. Okay. So that's it. We stop here.